All right, welcome everybody to the next installment of the New York Combinatorics Seminar. Our speaker today is John Byrne from Delaware, who's going to tell us about Sidon sets. Take it away.
Okay. Thanks very much for the introduction and hosting me. And yeah, I'm going to be talking about directed even cycles and nonabelian Sidon sets. Everything in this talk is based on some joint work that I did about half a year ago with my advisor, Mike Tate. And so actually, I'll be covering these topics in the reverse order. So we're going to start by talking about Sidon sets.
Oh, okay.
Okay, sorry. Click. Did I click? Now try it. Okay. Okay, cool. No worries. So we're going to start by talking about Sidon sets. And so to give some historical background, right? The original notion was of a Sidon set in the integers. And so a subset of the integers is called a Sidon set if for any distinct pairs of elements of your set, you have a distinct sum. So in other words, all solutions to the equation a plus b equals c plus d for elements coming from the set A must be trivial. In this case, meaning that we have the same set of elements being added on each side of the equation. And so this notion was introduced by Sidon in 1932. Excuse me, Sidon was working in Fourier analysis. And so he showed that if you have certain trigonometric polynomials that whose terms are defined from a Sidon set, then you can obtain this bound on the fourth moment. So this is just some hint of the original motivation. But in this talk, rather than looking at Sidon sets in the integers, we're interested in Sidon sets inside of finite groups. So for now, let gamma be an abelian group. A Sidon set is defined in exactly the same way. All solutions to the equation a plus b equals c plus d, where the elements come from your set, must be trivial. But because we have a finite group, we can ask what is the maximum size of a Sidon set inside of a group. And so in order to obtain a good upper bound, we're going to observe this equivalent formulation of a Sidon set. So you can show that if all of the distinct pairs receive distinct sums, then any distinct ordered pair of elements from your set receives a distinct difference. So any set satisfying this equation is also a Sidon set. But then the number of ordered pairs of distinct elements of a Sidon set must therefore be at most the number of non-identity elements of the group. And so this is a general upper bound on the size of a Sidon set in an abelian group gamma. And as it turns out, this bound is tight. Okay, so if we care about the asymptotics, we get that the size of a Sidon set is roughly the order of the group to the power of 1/2. But in fact, there exist constructions of Sidon sets that meet that upper bound exactly. So in 1938, Singer constructed perfect difference sets inside of these cyclic groups, which are equivalent to Sidon sets, which have maximum theoretical size. And then following that paper, there have been a number of classical constructions of Sidon sets in various abelian groups. So you can tell just by, looking at the groups that these dense Sidon sets live in, that they're, all of these constructions should have something to do with finite fields. And recently, there's been this unifying result of Eberhard and Manners that showed this uniform way of constructing a Sidon set, which obtains all of these classical examples as special cases. So they conjecture that any dense Sidon set has to be obtained from this theorem in some way. But so far, all we know is that these known constructions of dense Sidon sets are precisely the Sidon sets that you can construct using their theorem. Okay, so a few reasons that people care about Sidon sets. If A is a Sidon set in the group gamma, then the set of translates of the Sidon set by all the elements of the group forms a partial linear space. So this, as a set system, the intersection of any two of these sets has size at most 1. And therefore, that means that if we have a Sidon set that meets this theoretical upper bound, then the set of translates forms a projective plane. So there's sort of connections in both directions between Sidon sets and projective planes. For the purposes of this talk, we're most interested in the applications to extremal graph theory. So sort of as a result of this fact, if you have a dense Sidon set, you can use that to construct a dense C4 free graph, meaning the number of edges is on the order of n to the power 3/2. And in fact, for certain particular values of n, the number of vertices in the graph, the largest known construction of the Sidon of a C4 free graph on that number of vertices comes from Sidon sets. Okay, finally, Sidon sets in general groups, they're related to these questions about taking some given graph and trying to embed it as an induced subgraph of some Cayley graph. And okay, so these are a few of the motivations for looking at Sidon sets. Okay, so we can generalize Sidon sets by asking, what if instead of forbidding these equations with two terms on each side, we forbid any distinct k elements receiving the same sum. So a subset of a group is called a BK set if all solutions to this equation, the sum A1 through AK equals the sum B1 through BK, must be trivial. Here, what trivial means is that we can rearrange the terms of one side of this equation to obtain precisely the other side of the equation. So another way of saying that is all distinct k multisets of your set receive distinct sums. Okay, so again, if you're wanting to know about the maximum size of a BK set in a given group, we can show that this is at most something on the order of the kth root of gamma. And we know that this upper bound is tight up to a constant factor by a construction of Bose and Chava. Okay, unfortunately, this fact about Sidon sets giving rise to C4 free graphs does not extend to BK sets. So if you take, for example, the bipartite Cayley graph of a BK set, it will contain cycles of length 2k, which is what we would like to be false. And this essentially arises because of commutativity of the elements of the BK set. So one way to try to fix this problem is by looking now inside of nonabelian groups. And we say that a subset of a nonabelian group is an SK prime set. This is our own notation. If we forbid this equation, so A1 B1 inverse through AK BK inverse equals the identity. We say that all solutions to this equation must be trivial. Where here by trivial, we mean that some element appears directly next to its inverse in this expression. So this turns out to be precisely the equation that you need to forbid in order to guarantee that the bipartite Cayley graph of the set A is a C2K free graph. I mean, in fact, it has girth greater than 2K. But these things are hard to construct, of course, because it's a very hard open problem to determine the order of magnitude of the Taran number of the even cycle, right? So it would be very nice to construct these things. And there, in fact, some of the densest known constructions of C2K free graphs can be phrased in terms of constructing SK prime sets inside of certain groups, but these will not be the main focus of our talk. So instead, we're going to look at this other equation we forbid. So here, we take the same equation that we forbidden with BK sets, the product A1 through AK equals the product B1 through BK. But now instead of demanding that we have the same multiset on both sides of the equations, we demand a stronger condition that the tuple A1 through AK equals the tuple B1 through BK. So we have equality in each coordinate. Okay, so I'd just like to point out that, right, if you have an abelian group, then these two equations from an SK prime set and from an SK set are equivalent. But in a non-abelian group, these are very different things. Okay, so naturally, what we're interested in is what is the maximum size of an SK set in a given group? So we'll call that MK of gamma. This is the main function we're interested in this half of the talk. And there's a very simple universal upper bound on MK of gamma. The number of K tuples coming from your set must be at most the number of group elements. So MK of gamma is at most the kth root of gamma. Okay, so we'd like to know whether this is tight. And the best currently known is that this is tight up to some constant factor. So in 1995, Odwischko and Smith constructed a sequence of groups G and a sequence of sets inside of these groups that showed that Okay, essentially the MK of this group G is on the order of magnitude of the kth root of the order of G. But the way they obtain this construction is somewhat interesting, so I'll say a little bit about it. The group here is a semi-direct product of the cyclic group of order p to the k minus 1 for a prime p with a cyclic group of order k. And the way this construction works is that they start with a known construction of a BK set, which lives inside of zp to the k minus 1, and translate a certain subset of this BK set into a coset of zp to the k minus 1 inside of this semi-direct product. Okay, so obviously I'm skipping most of the details, but it's interesting that they're able to start with the BK set, right? And then somehow upgrade it to have this stronger property. So let me just mention now, so these are still the densest known construction of SK sets. So an interesting open question would be, are there truly dense SK sets in the sense that this universal upper bound is asymptotically optimal? Okay, so to begin with the new constructions that we have, the first thing we're able to show is that there exist SK sets of order roughly n factorial to the 1 over k in the symmetric group and in the alternating group. So here we have this error term in the exponent. So you can think of this as being equivalent to like the kth root of n factorial divided by some exponential factor. This is quite a simple construction. So first we just begin with the Awishko-Smith construction. Really, it can be any existing construction of an SK set in any group. So let A be that SK set. And we're going to consider permutations of the elements of this ambient group. And we want precisely those permutations such that for every group element G, pi of G equals G times A for some element A of the original SK set. So it's relatively straightforward to show that this set of permutations is an SK set in the symmetric group on gamma. And so all that is left to do is to count the number of these permutations. And it turns out that you can write the number of these permutations as the permanent of some matrix. This matrix is essentially the adjacency matrix of the Cayley graph of A inside this group G. And because this matrix M is a multiple of a doubly stochastic matrix, the Gorachev-Felikman theorem or the van der Waarden conjecture gives this general lower bound on the permanent of M, which tells us what we want. So again, this is a very simple argument, but it's kind of interesting that we can blow up any existing SK set in order to an SK set in the symmetric group. And in fact, this works. You don't even have to start with an SK set here. You can start with, for example, high girth graphs or certain digraphs. So you can take a number of different objects and kind of blow them up to an SK set in the symmetric group. And then, okay, we can also extend this to the alternating group with a simple argument. Okay, so that's the best that we know for the symmetric group. So next we were interested in looking for constructions of SK sets inside of groups which are direct products of the form gamma times gamma. And the reason for looking inside of groups of this form is because, well, it was sort of in a loose analogy with the known constructions of abelian Sidon sets, which often appear in groups of this form. So intuitively, we thought that maybe working with 2 coordinates would make our job easier. And it turned out that this is true, of course, for a very different reason, because we don't have any of the tools from finite fields to work with. But first, I should mention this fact. So if we have 2 SK sets in different groups, then the Cartesian products of those SK sets is again an SK set. So this is something that is not true in the case of BK sets. So actually, if we want a lower bound on M2 with Sn times Sn, we can just apply the construction for Sn that I showed on the previous slide and find the correct exponent up to some error term. But we can improve on this considerably with an explicit construction. So what we show is that M2 of Sn times Sn is at least n minus 1 factorial, and we showed something similar for An. So essentially, instead of dividing by an exponential factor, we divide by a linear factor from the trivial upper bound. And another thing which I should mention is if you really dig into the content of this error term, the best known lower bound for an S2 set inside of Sn is actually obtained by simply embedding this construction inside of Sn. This obtains a better error term than what you get from the previous construction. Okay, so to prove this, right, so it'll be a result of a more general construction, but I'll show you the particular case for Sn first.
Sorry, could you just restate what you're saying in a more, or what you're about to prove? Just say it, like expand out what M2 is.
Yes.
You know, just so I know what's about to happen.
Yeah, so here we're saying that there exists an S2 set inside of Sn times Sn of order of size n-1 factorial.
Right. And right.
And so an S2 set is a set where any distinct pairs of elements have distinct product.
Where the order matters.
Where the order matters, yes. Okay, so we start by taking some special element pi. You can take pi to be any fixed cyclic permutation. So we'll just take 1 through n. And we'll define the set B to be all of the permutations that fix the element 1. So we just take the stabilizer of some point. And we claim that A is going to be an S2 set. So A is the set of all elements of the product group of the form B comma B pi, where B belongs to B. So why is this an S2 set? Well, if we suppose that we have an instance of this forbidden equation where the elements come from A, then looking at each coordinate, we get that AB equals CD and A pi B equals C pi D. Okay, so we solve for B in each equation, and we get that A pi A inverse equals C pi C inverse. So in other words, for this fixed element pi, we have that the conjugate of pi by two different elements of the set B gives you the same thing. But we constructed the set B precisely to avoid that situation. So, okay, applying what does conjugacy look like in Sn? Well, this means the cyclic permutation A of 1 through A of n equals the cyclic permutation C of 1 through C of n, but they both fix 1. And so now this is enough to say that actually A equals C, and therefore B equals D. And so we only have trivial solutions to this equation. So this is how the construction works, and you can kind of see how this generalizes whenever we have this conjugacy property that I talked about. So more generally, if we have any group gamma that contains a special element pi and a special subset B, where for any group element G, the number of B such that the conjugate of pi by B equals G is either 0 or 1, then the set of all these ordered pairs is an S2 set in gamma times gamma. So, okay, the moral reason why this works really well for Sn is because Sn has a very large conjugacy class, right, in all of the cyclic permutations. Okay, so I can talk more about this at the end if we have time. So let's turn to upper bounds on SK sets. First, I'll present as motivation a simple upper bound. If we have a group that contains an abelian subgroup of index 2, then I claim that we can improve the trivial upper bound by this constant factor. So if this entire square represents our group, let's say that this should appear as blue, so everything in this gray blue is our abelian subgroup. And suppose we have some SK set inside of this group. So the SK set will be all these red squares. Well, you can't have a large SK set inside an abelian subgroup, right? Because as soon as you have two elements in there, then you have, right, AB equals BA. And this is a forbidden equation because you can just multiply K minus 2 A's on each side. Right. But this shows that you can only have one element of your SK set in the abelian subgroup. So all the rest has to be in the coset. And then if we take the K product of any K things from this coset, they all land in the same coset. So essentially we have only half the space of the group to work with. So when we repeat this counting argument that gives you the trivial upper bound, we gain this constant factor. So the next question we wanted to ask is, can we repeat this argument where instead of having an abelian subgroup of index 2, we have an abelian subgroup of some fixed index, say h? Okay, so there's a couple difficulties when we try to do this generalization. So first of all, we don't know what the quotient group looks like, right? In the previous argument, it's very convenient that the quotient group is automatically Z2, but we need to have some argument that works no matter what the quotient group is. And then secondly, rather than forcing almost the entire SK set to belong to the same coset, in this situation, we have instead some distribution of your SK set across all of the cosets of this abelian subgroup. Now, it turns out that the information we need in order to generalize this argument appeared in this proof of this theorem of Dymowski. So in 1992, Dymowski showed that actually the trivial upper bound has to always be a strict inequality as long as the group is non-trivial. So MK of gamma is strictly less than the kth root of gamma. And Dymowski used this, proved this using representation theory. And so we were able to generalize his argument to show what we want. So, but basically the key lemma that we extracted from Dymowski's argument says that if we have some function such that the convolution of f is almost constant on a group, then the function f itself has to be almost constant. And in particular, f of 1 cannot be too small. And so the way we apply this is that f of 1 will correspond to the proportion of your Sidon set, which belongs to the abelian subgroup. But if this is not small, then we obtain a contradiction. So what we're able to show using this is that if we have a group with a normal abelian subgroup of some fixed index h, then MK of gamma is at most 1 minus epsilon times the upper bound. So we improve it by some small multiplicative constant. Unfortunately, we require the assumption that k is even. There's this one technical step in the proof where we need this assumption, but I believe that it also works for odd values of k. Okay, so a few open questions about SK sets. It seems very natural to wonder about the value of MK of Sn. So there's a gap between the upper and lower bound, which is exponential in n, and it would be interesting to see improvement from either side. I don't have a guess as to which is correct. Okay, so Dymowski showed that MK of gamma is strictly less than gamma to the power of 1 over k. I think that it's possible that this could be pushed a little bit further. So could we possibly show something like strictly less than gamma minus 1 to the power of 1 over k? There are some interesting graph theoretic questions that are related to directed Moore graphs that kind of appeared as a parallel direction of research, and the connection to SK sets seems to have been missed. So it seems to me that it's possible that some improvement or perhaps characterizations of these very large SK sets could be possible. And then finally, it seems natural to me to guess that if we have a group of the form gamma to the n, then the maximum size of an SK set in this group should not be too large. The intuitive reason for believing this is that there's kind of too many commuting pairs inside of this group. But it seems that using that fact alone is not enough to prove that this is the case. So I would not be surprised if I was wrong to guess that this inequality holds. Okay, so we turn to the second part of the talk. So applications to extremal graph theory. This won't appear, strictly speaking, as applications, but sort of the graph theoretic version of the question we asked. So I'll explain why this happened in a minute. But basically, so one of the main motivations for studying Sidon sets is to obtain C4 free graphs, right? If we have a Sidon set in a group, then the bipartite Cayley graph of that Sidon set gives you a C4 free graph. So we have this other type of additive object, an SK set, and it's natural to ask, what are the graphs that we can forbid using these things? So it turns out that here it's more natural to look at the directed Cayley graph rather than the bipartite Cayley graph. So we don't care about ensuring that we have an undirected graph anymore. But we simply ask, right, what are the forbidden directed subgraphs of the Cayley graph of an SK set? And so from the definition, what we get is we can't have something like this picture. So here, let's assume that K equals 5. Then this orange directed walk represents one product of 5 elements of your group. And the blue directed walk, which starts in the same place and ends in the same place, represents another product of 5 elements of the SK set, which has the same product, right? So this is actually impossible. So we don't have any graphs of this form. This is a whole family of graphs that I call FK. But then one subfamily of these graphs that I'm particularly interested in will be those graphs where there's no overlap in the middle, right? So this is the underlying undirected graph is just an even cycle. So I'll call like this graph, for example, is C44. And we're interested both in forbidding individual graphs as well as the whole family C22 all the way up through CLL, say. Okay, the question we're going to ask is, how large can the minimum out degree of an FK-free digraph be, or a CLL-free digraph? So initially you might say, well, why not just try to maximize the number of edges? It turns out that you can forbid both of these graphs in a sort of trivial way when trying to maximize the number of edges, namely just take a complete bipartite graph and direct all edges from the left to the right, right? So then in this graph, we forbid even just a directed walk of length 2. So in some sense, it's not natural to ask for the maximum number of directed edges in a digraph forbidding these, but the minimum out degree will give us a problem that looks more similar to the undirected Tehran problem for these graphs.
Do you require A to be generators of the group?
Do we require?
Usually
No.
no. The graph the age.
In this case, we don't require, so right, we'll get a disconnected graph if A is not a generating set. But I think it's just as meaningful to consider the problem if it's not a generating set. But I think that's sort of it. In all cases that we care about, it should be a generating set. Okay, so let's create a name for this problem. So if F is a family of directed graphs, I'll call M plus NF the largest possible minimum out degree in an F-free directed graph with n vertices. So just to kind of convince you that this is not totally contrived, well, there's a small typo here, but Kacheta and Hagfist conjectured that if the minimum out degree of a directed graph is at least the ceiling of n over L, then you have a cycle of length at most L. So this should be C3 through CL here instead of just CL. But these functions have shown up in other language before. But one recent result, which is closer to the particular cycles that we're studying, comes from this paper of Kelly, Kuhn, and Ostis. So they showed that if C is any balanced cycle, and we have a C-free directed graph, then either the minimum in degree or the minimum out degree is small O of n. So what is a balanced cycle? So we have some cycle, and we have some orientation of its edges, and I say that it is balanced if, as you traverse the cycle, the number of forwards edges equals the number of backwards edges, right? So in particular, these CLLs that we're considering are balanced cycles. Okay, so we can think of our results as like an improvement of this where we're actually able to obtain the order of magnitude for certain cycles. Okay, so firstly, we look at the family FK and the family C22 through CKK, and it turns out that this n plus function in both of these cases is on the order of n to the power 1 over k. So this should not be surprising. This is essentially a directed version of the even cycle problem or the problem of constructing graphs of high girth. But it turns out to be much simpler or easier in the directed case than in the undirected case. So like for FK, there's an upper bound which is exactly n to the power of 1 over k, which is sort of immediate. You can just take the k iterated neighborhood of a single vertex. For the lower bound, this is initially, we thought of it as an application of the existence of these SK sets. right? Because you can just take the Cayley graph of an SK set. But it turns out that there's a couple constructions that actually give you something better, and we get the exact asymptotics of this m plus n of fk. So really the only new part of this theorem is that these two functions have the same order of magnitude. What we found much more surprising is that if we take one particular cycle CLL, rather than the whole family of length up to k, then it turns out that the asymptotics of m plus is on the order of n to the 1/2, regardless of the value of L. And so one of the reasons this is interesting is because that means that, right, for this family C22 through CKK, then we have an example of a family of directed graphs where this extremal function suddenly jumps up a lot when we take any particular graph in the family. And if we look at the undirected version of that problem, this property is conjectured to be impossible by Erdős and Shimonovich.
What CLL is when you have a number of arrows one direction matching the arrows in the direction cycle.
It's one case of that. The CLL is where we have one directed path of length L and another opposite directed path of length L.
Specific one.
Yeah. Thanks. Okay, so right, naturally it would be nice if there were some way to obtain some undirected version of this, like from this construction, but it seems that that would be probably impossible. So, okay, so what is the construction? The lower bound is really what is kind of new here. So I'll talk about the lower bound. Here's a picture of the lower bound construction where we're forbidding this particular CLL, C44. And okay, so I'll talk about how this graph is defined, but first let's just convince ourselves that this picture does not contain a C44. Well, let's suppose that the leftmost vertex here were embedded where I place that red vertex. Then we have to have one path of length 4. Doesn't really matter because it's symmetric. And then we have to have another path of length 4. But because of this transition point on these vertices that I've labeled W0, we're forced into a different component of that portion of the graph, and there's no way to complete the cycle. And then the kind of length of this middle portion of the graph is chosen so that no matter where we put this initial vertex, you're forced here to have the two paths go into different components and you can't complete the cycle. So it should be noted that this construction does contain C33 and it does contain C55. Okay, and now, so to obtain an infinite sequence of these graphs for the fixed value of L equals 4, we'll just add a vertex to each part, and we'll also multiply the number of parts. So formally speaking, how is this construction defined? There's two sets of vertices, the V's and the W's, and each of these parts is indexed by 3 coordinates. And whenever you traverse an edge in this graph, the I coordinate increases by 1. And then either the J coordinate varies freely and the K coordinate is fixed, or vice versa, where if you're in the V vertices and the J coordinate varies freely and the K coordinate is fixed, and if you're in the W's, then it's the opposite. And at some point you transition from the V's to the W's. Okay, so this is not enlightening, but this is how these graphs are defined, and they forbid CLL. Okay, so the last thing I want to talk about is this problem about Hamilton paths. So I'll have to give some setup. We say that 2 Hamilton paths on n, I mean 2 Hamilton paths in the complete graph on n vertices, create a 2-part L cycle if their union contains CL as a union of 2 respective subpaths. Okay, what does this mean? So for example, here is one Hamilton path on 8 vertices, and here's another. And here is the C6 that is contained in their union. And this is a union of 2 respective subpaths because we can think of it as here's orange and then blue in the rest. So those are 2 paths that give you the site. So these 2 Hamilton paths create a 2-part C6. On the other hand, if we take this Hamilton path and this Hamilton path, again, here's the unique C6 contained in their union, but here you can't get it as 2 subpaths. You have to go like orange, blue, or something like that, right? Okay, so what is the problem? The problem is to determine the maximum size of a family of Hamilton paths in Kn, any 2 of which create a 2-part CL. So this was first posed in this paper of Cohen, Facchini, and Kerner. And in that paper, they showed that if we want to create a two-part C4, then this maximum is roughly root of n factorial. Okay, so our goal now is to extend the upper bound in this theorem to arbitrary values of L. And we're able to show that for any, I should say even L here, m hat n L is at most root of n factorial. But there's still a gap between the lower and upper bounds here. So I should note that this m hat n L is bounded below by roughly the Lth root of n factorial. So, and again, I don't have an intuition as to which of these is correct. If L is odd, then you can get roughly n factorial. So, okay, this is going to be an application of this construction that I showed you a minute ago, but we'll prove this through this well-known folklore result. If G is a vertex transitive graph, then the product of the independence number and the clique number of that graph is at most the number of vertices. And so the way we will apply this is by defining an auxiliary graph whose vertices are all of the Hamilton paths in the complete graph. And we want to construct a family of Hamilton paths such that no two of them create a two-part CL. And so if we can construct such a family P, then the size of P times this function that we're interested in is at most n factorial. So a lower bound on P will give us an upper bound on m hat. Okay, so to construct such a P, we'll start with the graph GLM that I defined. We'll let n be the number of vertices in that graph. And we need to count the number of directed Hamilton cycles in this graph. Now, it turns out that we can do this exactly. It turns out to be related to the number of Eulerian circuits in the bidirected complete bipartite graph. But what matters is that this is asymptotic to roughly root of n factorial. And then we ask, okay, so we have this family of directed Hamilton cycles. Now that we have the family of Hamilton cycles, we can delete an edge from each of them to get a family of paths. And moreover, we can forget the orientations of the edges and just consider this as a family of undirected Hamilton paths. And we ask, what do we get from the fact that they came from the graph GLM? Well, because this graph is, I should not say CLL free, I should say CL/2 free. So there's just a mismatch of the parameters here. But at any rate, we get that no two of its directed Hamilton paths can create a two-part cycle of this type, where the lengths of the two subpaths are equal, which makes sense because this is the directed even cycle that is forbidden in this graph. But it is possible for them to create other types of two-part C2Ls. But it turns out that these other C2Ls are sort of unbalanced in some sense that we can easily filter them out without affecting this error term. And therefore, at the end, we have the family that we want of order roughly root of n factorial. And so we're able to get this result. So I thought it was interesting that we have this question that's fundamentally about an undirected graph theory problem that we're able to take a directed construction and prove some bound on it. Okay, so let me end with some open questions about these problems on directed graphs. So we've considered one possible orientation of an even cycle where we have two subpaths. To my knowledge, there's only one other orientation of the even cycle where the order of magnitude of this function is, well, known would not be the correct word. But if we consider the anti-directed C2L, where the edges alternate forwards, backwards, and so on, then you can show that the order of magnitude of this m plus function is equal to the Turan number of the corresponding even cycle up to some linear factor. And so one of these orientations is sort of equivalent to this hard and long-standing problem. The other is known from this relatively simple construction. So it's kind of natural to ask what happens in between. And ideally, perhaps we could show that if you take any balanced orientation of this of the cycle, then either there's some undirected graph problem that this is equivalent to, or we can figure out the order of magnitude. Okay, I now know that the answer to this question is no. But so the point was, okay, what is the largest minimum out degree of an n-vertex F-free digraph? We know that this function is on the order, there is asymptotically n to the power 1 over k, what if we impose the restriction that your construction is vertex transitive? Because we get vertex transitive if you use an SK set. But it turns out there's a way to modify the original construction to get something vertex transitive. So the answer to this question is no. And okay, I think I'll stop there for questions. Thank you very much.
Thank you. All right, questions in person?
I don't think I've seen this M plus thing defined before. Was that defined as interest in itself, or as you said, it's connected to a terrain number? Is that why it was looked at?
Yeah, so the original
This min, would it be the greatest algebraic thing? Yeah, I don't, because why do people consider that parameter, how that parameter comes?
So I'll say, okay, the original, the reason that we were interested in it at first was because, okay, we noticed that the Cayley graph of an SK set forbids this particular orientation of an even cycle. So we wanted to find an extremal problem where this construction is good, kind of working in reverse. And it turns out that the directed Tehran problem was not the right question to ask, but it works with this minimum degree thing. However, in general, so like, again, this, the Kacheta-Hagfist conjecture, there's a large literature on that problem asking about the minimum out degree that forces a cycle of length. Excuse me, this is the wrong slide, but the minimum out degree that forces a cycle of length up to L. In this paper, they also look at the minimum out degree that forces a cycle of length exactly L, which turns out to behave slightly different. Yeah, none of in this paper, I think they call it something else, like D directed of N or something like that. I'm not sure about applications of these problems to other areas, but all I can say is that, like, under different terminology, this function has been considered in a fair number of works.
Any questions on Zoom?
Oh, I'm
Oh,
sorry. They wanted the screen to be tilted up for
you
a
didn't
while.
see that. Okay, whoops. That was a long time ago.
Sorry about that.
Let's see.
So as far as the undirected terrain problem for even cycles, like is there any hope? Is there any like, oh, if we could just do this, then it might apply to that? Like, if we could get a construction in these things, then we could do like, was that the original motivation for looking at this, or was it was more?
So I think the short answer to your question is no. So if you wanted to make an improvement on graphs forbidding even cycles, then you would have to construct SK prime sets, which are
That's right.
Right, these guys forbidding these equations.
Right. And that's maybe where you initially were looking or something, or very early.
So actually what sort of launched this project is we observed that if you take a bipartite graph that forbids C4 and take all the permutations that map elements along edges of this graph, then you get a Sidon set in the symmetric group. But it turns out that that's not only a Sidon set, but this stronger thing. And so we looked at SK sets after we realized that there's this blow up type construction. We do have a couple results on SK prime sets that are much less significant. So we have some probabilistic constructions of SK prime sets inside of nice enough groups. So we get, for example, that there exists an SK prime set inside the symmetric group of order roughly n factorial to the power of 1/3, which is kind of typical for probabilistic lower bounds on Sidon sets, getting this exponent of 1/3 instead of 1/2. But of course, there's no reason to use those constructions in order to construct even cycle free graphs, because you can just have a probabilistic construction of even cycle free graphs. What perhaps would be most hopeful is I wondered whether anything in this conjugacy construction, because this is the conjugacy construction is really the only new technique. If any of these ideas could be modified to give SK, well, either SK sets or S2 prime sets or SK prime sets. And I'm not convinced that it's impossible, but it seems much more difficult. Right, and just one more comment to add. So, and we also have an upper bound on SK prime sets. So looking at kind of the obstruction of having an abelian subgroup, in it, we showed that in an SK set, we can get 1 minus epsilon times the order, times the trivial upper bound, if you have this large abelian subgroup. But it's a much stronger obstruction in the case of SK prime sets. I'll actually skip ahead to the result here. So essentially, if you have a large abelian subgroup, not necessarily even normal, then actually the size of an SK prime set is bounded. So if we have an abelian subgroup with some fixed index, then the size of an SK prime set is bounded. And this is just because SK sets are translation invariant in contrast with SK sets. And so you can take the average size of the intersection of one of these translations with the abelian subgroup to get this bound. So we can say that if you want to construct SK prime sets, you better look in very non-abelian groups.
Yes. If you connecting the Sidon sets to the directed graphs via the Cayley graph, was the only connection was the fact that you might have two paths starting at the same place, directed and ending at the same place. That's the one thing that connects up the getting the same products for the graph thing. So you can do that. Is that once you have, is that the only sort of, and then once you move between that, then that's where you connect the results on the Cayley graph with the Sidon set, just having simply two. That's all. That's a whole point. Just two. You start someplace, move around, and you end at the same place. And different, and that will give you distinct, different products, same value, right?
Yeah.
That is the only connection point between. Is that right? The Sidon set thing you're doing and the graph thing we're doing.
Yes. So that, yeah, that is essentially the only connection between Sidon sets and directed graphs. Is so A is a Sidon set if and only if the Cayley graph of A forbids FK.
Right.
But I will add that if you have a directed graph that doesn't have these two paths ending at the same place, then you can take all of the permutations that map elements along directed edges of this graph and get a Sidon set in the symmetric group on those vertices. So we have the, again, like the blow-up construction, we can get this kind of like two-way connection between the graphs and the Sidon sets. Those are the only connections that I'm aware of.
And you were focusing on the one, it seemed like the CL comma L is one way of doing it. You could also imagine that the two paths come together. I guess they came together at some point for a while. I guess you're looking at the first place. They deviate and come back together. Why would you look at more complicated things besides the CLL? But yes, if you do get two paths starting and ending at the same place, you'll get CLL. I'm thinking out loud, right? That's why you're really focusing on that one in particular. Okay.
Yeah, so if you forbid, so you're taking like, you're saying, look at other elements of this FK family. Yeah, I mean, of course, if we have, for example, one path with three edges and another path with only one edge that goes to the same place, then it's unbalanced and we can immediately get minimum degree, which is linear. So it has to have this balanced in this condition. But yeah, I would guess that if they meet earlier, then what you would want to do is just consider this first cycle and take the GLM that forbids that. Yeah. But I have thought about considering other orientations. So for example, say you go forwards, forwards, backwards, backwards, forwards, forwards, backwards, backwards as an orientation of C8. And for a lot of such things, you can also get that this GLM graph forbids that. But it doesn't work for all of the balanced orientations, of course. So there's this project of looking at precisely the orientations of CLL or C2K that are forbidden in this graph. And then for other ones like the anti-directed one, I don't know. I think I have a characterization of like which orientations this doesn't work for, but I don't remember off the top of my head right now.
Anything else? All right. If not, let's thank the speaker again.
Thank you very much.
Okay. Thanks everyone for coming. We'll have another in-person talk next week, so please come by for that. All right. See you later.